So this is part 3 of this lecture course, and it is lectures on specialized topics. It may be in your research you'll only want to know about one of these specialized topics. It may be you don't want to know about any of them. But I'm going to tell you some half dozen specialized topics. And the first one is hyperbolic equations, where my advice was, if you remember, don't do it. They're a disaster for numerical solution of equations, are hyperbolic equations, because they just shift sideways the information. The velocity, or the concentration, the temperature, it's just moved around and it's not changing. If you had some diffusion, if you had some reaction, then it's okay because you're doing something. Right, so in the first half about hyperbolic equations, we went through the main issues about accuracy. Is it a first order accurate method? Is it a second order accurate method? Always stability. It's quite easy if you take a large time step for these systems, these algorithms are unstable. And then also we make a long wave analysis, assuming that the solution is varying slowly between the grid points, to find out what is the nature of the numerical error. And we find there is an artificial numerical diffusion or an artificial numerical dispersion. I should have said for the hyperbolic equations, you would normally never use finite elements or spectral methods, because the success we've had, which is a very limited success, is because we've been able to match up together the spatial representation and the time representation, and an interaction between the two enables us to do better. Right, so there's a list here of 6 algorithms and a record of what happened. The simplest, obvious one is unstable, always. There is the Lax-Friedrich, which is stable, but it is too stable, and the solution decays rapidly, spreads and decays. Upwinding, it was obvious we should have done upwinding, and if we do upwinding, it's better, it's stable, it's first order, it diffuses still, but not so badly. The problem with the Lax-Friedrich is that the numerical diffusivity gets bigger as you make smaller time steps. That really is a major problem. Then there's some second order schemes. Crank-Nicolson is implicit, where Lax-Wendroff is explicit, and there's a rather strange thing called an angled variable or a zigzag algorithm, which is explicit as well. And these second order schemes don't have diffusion, they have dispersion. That the short waves tend to travel slower than the long wave, so the main solution moves at one speed, and little waves, short numerical waves, move at a slower speed, so we develop spurious oscillations. But on the whole, these second order schemes did quite well. Okay. All that first lecture was about moving information sideways, and the information was smooth. I had 0 most places, and then there was a quadratic increase up to a maximum, so that my data, my initial condition, was continuous and had a continuous derivative. We're now going over to discontinuous initial conditions and find out what is happening there. Moving information u sideways at a constant velocity c, and it's a positive velocity. Later on we'll switch to some nonlinear velocities that vary with position and time. And the special feature about all this lecture is to have a discontinuous initial data, that the solution is 0.2 nearly everywhere, and there's just a little interval where it is 1. So it's a square wave. And it's important that it isn't 0, otherwise 0 doesn't do anything. And you know there's going to be problems when we had the dispersion methods, the second order methods. The error was delta x squared, but was the third derivative of u. This solution doesn't have a first derivative at the discontinuity. So our error estimates don't work. Okay, so this is the two best techniques we had, the angle derivative and the Lax-Wendroff method, applied to the initial condition, which you can see there's a square wave initially, and in time, it develops, in time one, it has developed all these wild oscillations at the front and at the back. On the other hand, the upwinding method, which was rather bad for continuous data, does not badly. So there's the initial square wave, and it is turned into a smooth solution, but it doesn't have nasty oscillations. So what was a bad method, the first order methods for smooth data, turns into be a good method with discontinuous data. So we need a new idea which somehow uses second order methods on the smooth part and uses first order methods on the discontinuous part. So we need a new idea, and the magic words in the subject are TVD, total variation diminishing. You'll see in a minute why this is a good idea. So you work for a solution which depends in space. You work out the total variation as being the sum of the absolute value of the difference between adjacent points. So if you do that, it ends up being, it's the sum of the absolute values between a minimum and a maximum, between a maximum and a minimum, between a minimum and a maximum. At least, that's right, as long as you've got a point at the minimum and maximum. And so that's the total variation. A total variation diminishing is that quantity decreases in time, or doesn't increase in time. So that at time step n plus 1, it's less than equal to the value at time step n. And if your algorithm has this property, it means that you can't get a new oscillation. You can't generate spurious oscillations because you'll produce new minima and maxima, and you'll contribute to this sum of the differences between the minimum and maxima. Right. On the other hand, where the solution is not oscillating, it's continuously increasing or continuously decreasing, a method that has this property will leave it as continuously increasing and continuously decreasing. It's not introducing new oscillations. Right. So that's what we would like. That's the property we'd like. And that is achieved by something called flux limiters. So the idea is the method, the algorithm, will be a low-order method plus a correction. And say the low-order method is upwinding, that behaves itself well in discontinuities. And then we have a correction, which gets us to Lax-Wendroff. But the limiting, so we think of the high order method as being a low order method plus an extra bit, the correction that makes it high order. And then the limiter will switch off the correction whenever we're in an oscillation. And the limiter will reduce the contribution from the correction. We'll only get half the contribution from the correction if the gradient is increasing steeply. If it looks like we're about to go into a discontinuity, we'll begin to switch off the correction. Those corrections giving us all those spurious oscillations. So it means that the method is sort of first order because where there's big discontinuities, there we use just a first order method, but it sort of ends up being second order accurate because the regions where we have first order are rather small regions, and most of the world is smooth, where we're using our high order, first order plus a second order correction. We're using a second order method in most of the domain. Okay, so it's quite a good, clever idea. Right. So to write down this, the algorithm, you make a time step. So I've taken the delta t over there. So we've time stepped from level n to n plus 1. And we write it in a conservation form, so it's a divergence of fluxes. So there's a flux coming in at time level n, we calculate the fluxes, and there's a flux coming in from half a step forward minus the flux that's coming in behind at a half step backwards. So if we were to sum across the whole grid, the in and outs cancel except from the beginning and the end. That's what it's a conservation scheme. And for upwinding with the Lax-Wendroff correction, what we write is the flux is the upwinding flux. So what is coming in over level L plus a half is all to do with the velocity before, as long as the velocity is positive. So the positive is in that direction for you, yes, right. So if we want to know the flux at L plus a half, and things are moving that sideways, we use the value of u at L. So that's the upwinding, first order part. And then what you need to convert the flux to the Lax-Wendroff is you have to add this extra bit, but we don't quite add that extra bit. There's a very important u primed. So this is upwinding again, and it's the and that primed is the derivative, but we're going to limit that derivative by the derivative before. So the Lax-Wendroff uses the divergence of the gradient. You saw a second order correction, a second order derivative go in. So the red part, the second order correction, is going to use the derivative at L plus a half, the spatial derivative at L plus a half, but limited by the spatial derivative before. So if they're the same opposite signs, I'm in an oscillation, I won't do it. If the derivative at L plus a half is just a bit bigger than the derivative at L, I'll probably allow it. But if the derivative at L plus a half is much bigger, it looks like I'm going into a discontinuity, I won't allow that term. I'll switch off the correction term. Right. So we have one quantity, the derivative that we want to use, and a limiter, something we compare it with, a derivative at the point before, and we have to make a decision what to use. And there are many possibilities. There are two quite common. One is called min mod. So here we have A, that's the derivative at the point L plus a half, and then B is the derivative before. B is going to make some limit on whether we use A or not. So if they're of the opposite sign, we don't use this correction. We switch this term to 0. We switch off the correction. If this gradient is smaller than this term, so the gradient at this point is less than the gradient before, we're in a fairly smooth situation, so we use the true gradient. On the other hand, if the gradient here is bigger than the one before, we use the one before. And here's the result. So it's better than the upwinding on its own. Let me quickly go back to the upwinding on its own. There's the upwinding on its own. You can see the amplitude's coming down and it's spreading quite a bit. With this min mod limiter, the amplitude is still sticking at 1, and it's fairly steep there in the discontinuities. So we're treating the discontinuities fairly well, and in the smooth parts, we're treating them that rather well. So there's another one called Super B. So this is more complicated. So again, if the gradient at the point of interest is, we compare the gradient here with the gradient at the one point before, and if they're of opposite sign, I'm in an oscillation, don't do it, no correction. If the gradient here is less than twice that one, it's the gradient's increasing, but it's not increasing too much, so we allow it. So that's what all that arithmetic there is doing. On the other hand, if the gradient here is more than twice the gradient here, we use this one. Okay, you have to sit down and go through all these complicated expressions and find out they do exactly what I've told you. And then Super B's are just a bit better. It's just a bit steeper, and we're preserving amplitude. Okay, so that is for the linear advection with advection at a constant speed, and the corrections here have been written out for positive c. If we had this equation with a constant but negative velocity, then I think you want minus the modulus there. And of course, what is upstream here is the other one. For L plus the flux at L plus a half, if it's moving this way, you want to use the value u at L plus 1, because it's coming at you that way. Okay, so we'll now go to what is the fluid mechanics case where we have advection with u dot grad u. So the velocity at which we're moving sideways depends on u itself. It's a nonlinear term. It's a quadratic term. And in general, so I'm going to have a velocity that it moves at, which is called f prime, because I really want to have a conservation formulation. I want the flux to depend on u. So in order to get u dot grad u, I want the flux as being u squared, half u squared. Okay, so for our hyperbolic equation, there are two forms which are quite different. There is the one that looks like before, the propagation form, that the time derivative is the space derivative multiplied by a velocity, which is u prime, which depends on u. Or there's the conservative form, where we add up, we integrate across the domain, and we find that the change in the integrated value of u in time is due to the difference of what's coming in to what's going out. Exactly, there's no numerical error. And the conservative form is much better. Okay. So if you understand shock waves, you will know that if we have u on the left, which is bigger than u on the right, then this is going to go faster than this, so it's going to overtake it. So we have a propagating shock wave, and if you do a steady propagating shock wave, the speed at which the shock wave moves is the difference in the fluxes, the greater flux to the left compared with the flux to the right, divided by the different values. That's the. Does anyone here do shock waves? Has anyone had shock waves in their education? Thank you. So you would agree that's right. Sorry? Right, immediately. This should be UL minus UR. I'm glad I've got an expert. Okay, friction, UR. Okay, so I've solved with one of those nice schemes. Actually, that's not true. This is, now, with these nonlinear problems, you can just use upwinding. The reason you use upwinding is the formation of a shock wave, and I didn't talk about if this steps down instead, then there's a, okay, so if the levels were different, this would go away faster than this, and you form then a rarefaction wave in between. So forming shock waves, constantly having material catch you up, it sharpens up the gradient. You're doing something definite. In the other case, when the levels are different, when they're spreading out, the rarefaction wave is evolving in time because they're doing something definite rather than just moving information sideways. Well, they are moving information sideways, but they're just evolving. You can use a first order method. Because if the first order method would like to spread things out, well, that's just what you want to do in a rarefaction wave. First order methods spread things out, but the formation of shock waves is crowding material in and sharpening up your gradients. So actually this solution was with a just upwinding, and I've coded up in continuous black the conservation form, and in the dashed curves is the propagation form. And the interesting thing is, theoretically, the speed of the shock, as we had 1 and 0.2, if you do the arithmetic with the flux as a half u squared, you find the speed of the shock is 0.6. So theoretically, the speed of the shock should be 0.6. The continuous scheme with the conservative method has a velocity, which I've just calculated as being that value compared to the displacement of that in time 1, has a velocity of 0.59, which is good. Would get better if I had a greater spatial resolution. And the dash curves, that's the propagation form of the governing equation, has only gets to here, the furthest dash point in the same time, and it has a propagation speed of 0.46. There are many applications where you would like to know, you'd like the speed of the shock wave to be precisely right, rather than quite a large error here. For example, on a supersonic aircraft wing, you have a shock wave coming off, and where the shock wave is changes, gives you the difference between one pressure before it and one pressure after it. If you get the pressure on the wing in the wrong place, the aircraft will turn upside down. Okay, so to get the pressure distribution on a body that's going at a supersonic speed, you have to get the shock wave in the right place. Therefore, you desperately need a conservation method. Okay, really, because the Russians had such inadequate computers, they developed very good algorithms. So there's the Godunov method that they developed. I'll try and explain it. I've never coded it, and I wouldn't. It has 3 steps, R, E, and A. So R is reconstruction, E is to evolve it, and A is to average it. So you start at one time level with the solution, and then you reconstruct, you simplify the solution. Typically, you make it piecewise constant in each interval. The sophisticated version, second order version, would have piecewise linear in each version. Although the piecewise linear ones, they may still have a discontinuity at the boundary. May not be initially, but during the evolution they certainly would be. So you reconstruct the solution as being piecewise constant. Then you go to your governing complicated nonlinear equation, and it's simple if the information is constant. You know how to evolve it analytically. So this is called, you take a Riemann solution of your gas dynamics equations. So we have piecewise constants. Of course, they're discontinuities, and they're either discontinuities like this, which will form a rarefaction wave, or they're discontinuities this way round, which will form a shock wave. But we can involve the shock wave exactly correctly, and we can involve a rarefaction wave exactly. So we go one time step with using the analytic solution of piecewise constant for one time step. You have to make sure the time step is small enough so this shock wave doesn't get into the next grid block. So shock wave moves from the boundary into the next grid block. The rarefaction wave equally moves in both directions sometimes, but doesn't get into the adjacent, to the grid blocks beyond. So that's the evolution. And then, when we've got this new solution, we then average it within the grid blocks. So we've got the constant, piecewise constants ready to go back to the beginning. So actually, averaging is the same as reconstruction. So the third step's not necessary, because it's actually the first step. And then the middle step, which is all this complicated use of the analytic solutions for piecewise constant, is also not necessary. If you only want to know the constant values at the averaged values of the exact solution at the beginning of the time step, all you have to know is you had an average value at the beginning of the time step. What's the flux in and what's the flux out? And we can work out what the flux in and the flux out are. So I know the new average value. Those sort of ideas are really useful if you want to try and take this to the second order accuracy. So now this looks very complicated. I want to know what is the flux at position. So we had grid blocks with different L's, and I want to know what is the flux going from L. So I've got L and L plus 1. What's the flux over the midpoint boundary? And it depends whether information in this next part from L to L plus 1, whether information is going this way, in which case I want the flux according to that value, or if information is going that way, I want the flux according to that value. So that's what this is saying. That I want the flux according to this side if information, that's the speed of propagation of the information for that value is going that way, and if the information for this one, the downstream one, is going sideways. And this is just things going in the other direction. We then have the possibility that this information is going this way, and this information is going this way. That means I've got a shock wave on my hands. And the shock wave might be going this way, or it might be going that way. We had that formula for the shock wave. So if the shock wave says go this way, then it says use the flux from this side. On the other hand, if that formula for the shock wave says the shock wave is going this side, we obviously use the information from that side. And then you have another disaster. It may be that the information is propagating that way and that way. In which case it's telling you've got a rarefaction wave here, and the value of the flux you want is such that the information here is not propagating. So you want the flux according to a magic value of U star, where the information corresponding to the value U star is not propagating. It's quite complicated. If you're going to have a general law, the flux F depends on U in some complicated nonlinear manner. Okay, so this has been one-dimensional hyperbolic equations, and by now I can deal with arbitrary speeds of propagation. If it's nonlinear, I rather like conservation forms. If it's constant velocities, I like the high-order methods. And in some situations we want flux limited methods. So we can have a high order method where it's smooth and a low order method where it's discontinuous. There are generalizations of, there's a U gone missing in Godden. Never mind, I'm sure he has a U. Which have, the lowest order one has rather a lot of numerical diffusion, and by replacing piecewise constant by piecewise linear, you can improve that. And you quite quickly end up with something that looks like Lax-Wendroff. So you can go to generalize this to cases where U is a vector. That's what we want in gas dynamics. We have, even in one-dimensional gas dynamics, we have velocity, pressure, velocity, density, and temperature that we have to move. So we have three quantities, a vector of quantities we have to move. And what you have to do is to look at the speed of propagation. This is now a matrix, the derivative of the velocity with respect to the flux differentiated with respect to the components of velocity. And you want to diagonalize that to find the eigenvectors, to find out what combinations of the components of U are propagating at what speed, in what direction. And it can be nasty. You can get some information going that way and some information going that way. You can go to higher dimensions, which means that even with one quantity, we've in three-dimensional space rather than one-dimensional space. And then the Riemann solvers, which were used in the Goodenough method, are not available. And fluxes get a bit more complicated in 3 dimensions. And then I should say people in finite elements have tried to do something. So clearly fluxes are a good idea. And you can sort of try and do something about limited upstream fluxes. But you have to distribute those fluxes over the vertices in some way. And you end up producing a new type of numerical diffusion, which is numerical diffusion across the streamlines, where information was supposed to be moved along the streamlines. The finite elements tend to spread things across the streamlines quickly. Of course. Let me try and so I worked in an example. I have to do arithmetic in front of you. You don't ask a mathematician to do arithmetic. And I have U, which has a value 0.2 and 1. I have a formula for the velocity, which is F. Ready? So there's a half. Let's leave that outside altogether. That's easy. What is 1 squared? I can do that. Minus 0.02 squared. That's a little more difficult. I think that's 0.04. And then I've got 1 minus 0.2. Big breath. This looks like 0.9. This is going wrong at the moment, isn't it? Sorry?
So maybe an easier way just to keep it as half UN squared minus half R squared.
Don't do any arithmetic. Clever idea. So this is a half of UL plus UR. That is right. It must have worked out before. It would have done, wouldn't it? So I had 96 divided by 8, which is 12, and a half of it is 6. Okay, remember I'm going to start exactly at 11:30. So I can squeeze in. There's actually 2 lectures. The first one is on representation of surfaces, because fluid, in many fluid flows, the surfaces are not rigid and fixed, but there are the surface of the fluid, the water waves, for example, or liquid drops. And so the surface evolves, and we have to be able to describe the surface. And then there are some special fluid mechanics, either potential flow or Stokes flow, which are linear fluid dynamics. And for that, there is a very nice method that only lives on the boundary, called the boundary integral method. So it's suitable for evolving surfaces. So I'll describe that as well.